What is meteoric iron?
Meteoric iron is just what the name sounds like, it's iron that comes from meteors. For early civilizations, meteoric iron was one of the few available sources of relatively pure iron. That is, prior to when the extraction of iron from ore was discovered. Meteors containing meteoric iron are composed of mostly nickel-iron alloys. Iron meteorites often have a distinct appearance, and they are typically much easier to recognize than other types of meteorites. For this reason, they are discovered more often than other types of meteorites. Iron meteorites actually account for all of the largest meteorites that have been discovered.
What is a molecule?
A molecule is a set of atoms held together by chemical bonds. Molecules are the smallest units of a substance that behave as that substance. And separating the atoms of a molecule will change its properties.
What are the different phases of matter?
There are three phases, or states, of matter that you come across every day: solids, liquids, and gases. There is a fourth phase of matter, plasma, which is only naturally found in stars and elsewhere in outer space. The distinctions between the first three phases are usually made using bulk properties. Solids have a defined shape and volume, while liquids easily change their shape but not their volume. Gases have neither a defined shape nor volume.
How were herbal medicines discovered?
If we had the story of how each and every medicinal herb was discovered, each would likely be an interesting and unique tale. Unfortunately, the use of plants as medicine predates written human history by a few millennia. The earliest written records come from the great ancient civilizations of humankind.
Is it possible to see a single molecule?
With some of the largest single molecules, like polymers, they can actually be seen by the naked eye or through a microscope. Most molecules, however, are so small that a single isolated molecule cannot be seen with even the best microscopes. There is a physical limitation that prevents their observation with light, which has to do with the size of small molecules, lengths of ca. 0.1 to 1 nanometer, being significantly smaller than the wavelengths of visible light, 400 to 700 nanometers. Other techniques based on diffracting electrons off of molecules, measuring the force molecules exert against a very small metal tip. and other methods have been developed to image small molecules. But it's impossible to see most small molecules with light in the way that we conventionally see things.
What is iron smelting?
Smelting is a method for extracting a pure metal from an ore. An ore is a rock made up of metals and other minerals. In smelting, a chemical transformation may be used to purify the metal by changing the oxidation state of metals in the ore. We'll get into more detail on what an oxidation state is later in the book. The smelting of iron dates back to ca 1000 BCE, or maybe even earlier. And it typically involves first heating the raw material in a furnace called a bloomery. This produces a soft iron material that can be shaped. A hammer is often used to remove other impurities from the soft metal, before allowing it to harden to form a relatively pure form of iron.
What is alchemy?
Alchemy was among the earliest practices of a chemical science, and, in a way, it can be considered a predecessor to the modern science of chemistry. Alchemy is somewhat different than a modern science, though, in that it also has roots in mythology and spiritualism. Practitioners of alchemy were known as alchemists. Among the primary goals of alchemists were to find a method or material that could convert inexpensive metals into precious gold, as well as to find an elixir of life, which could make a person both youthful and immortal. Myths told of the existence of such materials and of the possibility of such feats. The goals of alchemists were based largely on these myths. In medieval times, alchemists could be found in many countries around the world, and those in different regions held somewhat different beliefs. In the Western world, people were still considering how to make metals into gold as recently as the late 1700s.
What is an ideal gas?
An ideal gas is a collection of atoms or molecules that do not interact with one another and occupy essentially no volume. While this is an idealized model, it turns out to describe many gases very well. The reason it works so well is that the atoms or molecules making up a gas are spread out far from one another, so that the intermolecular forces between them are extremely weak, they don't feel each other. This description leads to the ideal gas law, which is a relationship between the pressure, volume, and temperature of a gas. The ideal gas law allows chemists to predict how, for example, the volume of a gas will change as its temperature is increased. The equation for the ideal gas law is PV equals NkBT, where P is pressure, V is volume, N is the number of particles, atoms or molecules, T is temperature. And Kb is Boltzmann's constant, a fundamental physical constant.
How many different chemical substances have been discovered?
According to the Chemical Abstracts Service, CA, which is the world's largest authority for chemical information, the 70 millionth chemical compound was recently registered, announced December 2012. Today, new chemicals are being discovered and registered at a staggering rate. The 60 millionth chemical was registered only 18 months earlier.
What is the ionization energy of an atom?
The ionization energy of an atom is the amount of energy it takes to remove an electron from the atom. The process of removing an electron leaves the atom with an extra proton. Relative to the number of electrons, and thus creates a positively charged ion, known as a cation. The ionization energy can be thought of as a measure of how strongly an atom holds onto its electrons. In general, ionization energies increase from left to right across a period, though there are exceptions. Due to an increasing number of protons to attract electrons in the valence shell. Ionization energies decrease going down a group in the periodic table. Due to the valence electrons being farther from the nucleus, and thus more shielded from its positive charge. Note that the trends in atomic radii and ionization energy go in the same direction. Larger atoms tend to have lower ionization energies.
What determines which metals can be magnetized?
Chemists discuss magnetism in terms of three basic categories: diamagnetism, paramagnetism, and ferromagnetism. Diamagnetic materials have all of their electrons arranged in pairs, which, by definition, means that their spin magnetic moments must all be arranged in pairs and thus cancel each other out. For this reason, diamagnetic materials cannot be magnetic, and won't be influenced by magnetic fields. Paramagnetic materials have unpaired electrons, but in these materials the electrons spin magnetic. Moments cannot all be lined up in the same direction, which means that they cannot be strongly magnetic. Since they do have unpaired electrons, they can be influenced by applied magnetic fields, but not to the same extent as the third class, ferromagnetic materials. Ferromagnetic materials are the materials that can give rise to the magnets we're all familiar with. All of the materials that magnets can interact strongly with are ferromagnetic. In these materials, there are unpaired electrons whose magnetic spin can all be aligned in the same direction. Note that just because a material is ferromagnetic doesn't mean it must be a magnet, but rather just that it has the potential to be magnetized. Take a paper clip, for example, When you first pick it up, it's not a magnet. But you can turn it into a weak magnet by holding a magnet next to it for a short length of time. Some of the most common ferromagnetic substances are those made of iron, nickel, or cobalt.
What keeps an electron from crashing into the nucleus?
Opposites attract, so electrons and protons are attracted to each other, making it somewhat difficult to understand why an electron wouldn't just get as close as possible to the nucleus and crash into it. The key to answering this question has to do with the fact that electrons are very small particles, so they are governed by rules that don't apply to larger objects. As we've talked about a little already, electrons are best thought of as clouds of negative charge surrounding the nucleus. Their properties are governed by rules that describe the cloud as a whole, rather than as a single particle. It turns out that there is something favorable about the electron being spread out, or delocalized, around the nucleus. For reasons we won't go into in detail, when the electron's cloud gets packed closer to the nucleus, the energy associated with its motion, its kinetic energy, begins to rise, which makes the situation unstable. There's a balance between the stability associated with placing the electron close to the nucleus, the favorable positive-negative charge attraction, and that associated with spreading out the electron's cloud, to keep its kinetic energy low. This prevents the electron's cloud from getting too close to the nucleus or the electron just crashing into the nucleus.
What's the difference between alchemy and chemistry?
Let's ask Robert Boyle, who in 1661 published The Sceptical Chymist, arguing that experiments disproved the idea that the universe was composed solely of Aristotle's four elements. Boyle himself was an alchemist, in that he believed that one metal could be changed into another. But he was a staunch promoter of the scientific method and helped elevate chemistry to a science. So one could simply say that alchemy is a philosophy, while chemistry is a science.
Is everything made of molecules or atoms?
Basically, yes. The only material things that aren't made up of atoms or molecules are the subatomic particles that make up atoms. Anything you find around your house, office, or anywhere else is made of some combination of atoms that are on the periodic table.
How do the atomic radii of atoms change across the table?
The atomic radii of atoms generally decrease going from left to right across a period, and increase going top to bottom down a group, See graphic on next page. The increase in atomic radius going down a group is fairly straightforward to understand. Additional shells of electrons are added and they must surround the inner shells, resulting in an increased atomic radius. Though the number of protons in the nucleus increases going down a group, the inner shells of electrons serve to shield the valence shell from the attractive force of the nucleus, resulting in an overall increase in atomic radius. Moving to the right across a period, the number of protons increases, increasing the attractive force on electrons in the valence shell. Within a period, additional electrons go into the same valence shell, and an increasing attractive pull from the nucleus results in a more contracted valence shell, resulting in a smaller atomic radius. The situation is complicated by the rightmost group, known as the noble gases. But the atomic radius of these elements is typically not important as they are rarely involved in chemical bonds to other atoms.
What is the valence shell of electrons?
Electrons fill up orbitals in shells. The innermost shell consists of just one s-type orbital and can hold just 2 electrons. The next shell consists of one s-type and 3 type orbitals, and can hold 8 electrons. Higher shells consist of more and more orbitals and can thus hold more and more electrons. The valence shell of electrons is the highest occupied, or partially occupied, set of orbitals.
What are some common structures/geometries for molecules?
The study of chemistry has benefited greatly from knowledge of properties relating to the geometries and, especially, the symmetries of molecules. To get a sense of what shapes molecules adopt, it's worth taking a look at a few of the geometries that come up often in the study of chemistry. One commonly encountered geometry is that of a tetrahedron. Methane has the molecular formula CH4 and exists in a tetrahedral geometry, with angles of approximately 109 degrees between each pair of CH bonds. Linear geometries are also relatively common. Carbon dioxide has the molecular formula Co2 and exists in a linear geometry with a 180-degree angle between the co-bonds. One last geometry we'll look at here is a planar geometry. The molecule BH3 provides one example of a planar geometry. And in this case the BH bonds are separated by angles of 120 degrees. There are also planar molecules with 4 bonds in a plane. And in those cases the bonds are separated by angles of 90 degrees.
What is the atomic radius of an atom?
The atomic radius of an atom is defined as half of the distance between two atoms of the same element held together in a chemical bond. Not surprisingly, these are very small distances. For hydrogen, the smallest atom, the atomic radius is 0.37 angstroms, or 3.7 x 10 to 11 meters.
What is a substituent?
A substituent is an atom, or group of atoms, attached to a specific position in a molecule. For example, in the molecule 3-bromopentane, see drawing below. We could refer to the bromine as a substituent on the third carbon atom.
What makes something magnetic?
As we mentioned just briefly above, electrons have a property called a spin, or spin angular momentum, which can take on two possible values. This property, combined with the fact that electrons are charged particles, dictates that each electron has an associated magnetic moment, called the spin magnetic moment. In a macroscopic object, magnetism, or lack thereof, is determined by whether these spin magnetic moments are all aligned in the same direction. If all of the spin magnetic moments line up in the same orientation, the object will behave as a magnet. If the spin magnetic moments are oriented randomly, the object won't be magnetic. The trick is that only certain materials have the potential to exhibit magnetism. And we'll get to that next.
How do molecules interact?
The forces molecules exert on each other fall into a few main categories. Van der Waals interactions. Van der Waals interactions are the broadest group of intermolecular interactions. This includes basically all attractive and repulsive forces that don't involve ions. Charged atoms or molecules, or the rather unique situation of hydrogen bonding. Van der Waals interactions include forces due to the dipole moments of polar molecules, as well as interactions due to induced dipoles that can form even in nonpolar molecules. Ionic interactions. Another class of intermolecular attractions involves attractive and repulsive forces between pairs of ions, or between ions and neutrally charged atoms or molecules. These interactions are typically stronger than those in the van der Waals category. Interactions between pairs of ions are governed by Coulomb's law, while interactions between ions and neutral molecules are either ion dipole or ion-induced dipole interactions. Hydrogen bonding. A hydrogen bond is a strong interaction between a hydrogen atom and another electronegative atom, usually fluorine, oxygen, or nitrogen, that are not covalently bonded to one another. The hydrogen atom also must typically be bonded to an electronegative atom, usually oxygen or nitrogen. The origin of this strong attractive interaction is that a hydrogen atom bonded to an electronegative atom has a partial positive charge due to its lack of electron density. This allows the hydrogen atom to have a strong attractive interaction with electronegative atoms, or ions, which have partial negative charges due to their extra electron density.
How did ancient civilizations make bronze?
Tin had to be mined in the form of an ore and then purified through a process called smelting. Once the tin was pure, it could be added to molten copper. In whatever ratio was desired, to make bronze for use in things like tools and weapons.
Can elements be converted into one another?
It is possible for atoms of one element to become atoms of another element. One way this can happen is any fission process that results in the loss of one or more protons from a nucleus. The joining of two nuclei to form a single, heavier nucleus is also possible, and this process is known as fusion. Both fission and fusion can result in the creation of new atoms with different numbers of protons than were present before the reaction. These processes are often difficult to control in a laboratory, however. So it's mostly only in specific cases, such as energy production, that chemists and scientists in related fields devote a lot of time to these nuclear reactions.
What's a solvent?
In chemistry, a solvent is a liquid, though it can be a gas or a solid. But forget about that for now, that other chemicals are dissolved in. These other chemicals can be called the solute. The solute and the solvent can together be called a solution. Take salt water, water is the solvent, salt is the solute. And we can refer to the salt water as a solution.
How did pharmaceutical science get started?
Paracelsus is credited with being the first person to use chemicals in medicine. Before Paracelsus, people believed that illness and disease were caused by an imbalance in the patient. Hippocrates thought it was an imbalance of the four humors: blood, phlegm, black bile, and yellow bile. And Galen furthered these ideas by assigning a symptom to an imbalance of each of Hippocrates' humors. These theories supported the use of medical techniques like bloodletting. Paracelsus believed that illness was the result of something from the outside world attacking inside one's body, and that some of the illnesses could be cured by chemicals. He is also known for proposing the basis of toxicology, namely that dosage was critical to whether a substance was poisonous or not.
What was the first chemistry textbook published?
Although numerous chemistry texts exist before it, Alchemia, published by Andreas Libavius in 1597, is considered to be the first organized chemistry textbook. Libavius, born in Halle, Germany, in 1555, was a chemist and a medical doctor, and also served as a schoolmaster at the end of his life. In addition to his noteworthy textbook, Libavius is significant in the history of chemistry for further advancing the discipline away from the realm of magic, the occult, and alchemy toward a teachable, logical, and scientific discipline.
What is plasma?
Plasma, the fourth state of matter, is a gas where some amount of the particles have been ionized. As little as 1% ionization leads to very different properties for plasmas than gases, including increased conductivity, like lightning, and magnetization.
What is plasma?
Plasma, the fourth state of matter, is a gas where some amount of the particles have been ionized. As little as 1% ionization leads to very different properties for plasmas than gases, including increased conductivity, like lightning, and magnetization.
Are there plasmas in our daily lives?
Plasmas are found in fluorescent lights and neon lights. If you've ever seen a Tesla coil at a science museum, the arcs of light that they produce are plasma, as is lightning. Plasma TVs and plasma lamps are correctly named, both generate light using plasma, similar to fluorescent lights.
Are there plasmas in our daily lives?
Plasmas are found in fluorescent lights and neon lights. If you've ever seen a Tesla coil at a science museum, the arcs of light that they produce are plasma, as is lightning. Plasma TVs and plasma lamps are correctly named, both generate light using plasma, similar to fluorescent lights.
What is a phase diagram?
A phase diagram shows the phases of a particular substance as a function of temperature and pressure. An example for a single component phase diagram, as in not a mixture, is shown above. Phase diagrams also exist for mixtures, but these get very complicated very quickly.
What is a phase diagram?
A phase diagram shows the phases of a particular substance as a function of temperature and pressure. An example for a single component phase diagram, as in not a mixture, is shown above. Phase diagrams also exist for mixtures, but these get very complicated very quickly.
What is a triple point?
The temperature and pressure at which three phases of a substance are in equilibrium is known as a triple point. The three phases can be solid, liquid, and gas, but can also be two solid phases. Different arrangements of the molecules in the solid and a liquid phase.
What is a triple point?
The temperature and pressure at which three phases of a substance are in equilibrium is known as a triple point. The three phases can be solid, liquid, and gas, but can also be two solid phases. Different arrangements of the molecules in the solid and a liquid phase.
What is a critical point?
A critical point is a combination of temperature and pressure. Values above which a phase boundary no longer exists. There are liquid-liquid critical points above which the two liquid phases become miscible. And also liquid-gas critical points above which the boundary between the liquid and gas phases disappears and the substance becomes supercritical.
What is a critical point?
A critical point is a combination of temperature and pressure. Values above which a phase boundary no longer exists. There are liquid-liquid critical points above which the two liquid phases become miscible. And also liquid-gas critical points above which the boundary between the liquid and gas phases disappears and the substance becomes supercritical.
What is a supercritical fluid?
Above its critical point, a given temperature and pressure combination. A substance behaves like both a liquid and a gas and is called supercritical. Supercritical fluids are very good solvents, like liquids. And as a result many modern chemical processes use them.
What is a supercritical fluid?
Above its critical point, a given temperature and pressure combination. A substance behaves like both a liquid and a gas and is called supercritical. Supercritical fluids are very good solvents, like liquids. And as a result many modern chemical processes use them.
How is coffee decaffeinated?
Consider the chemistry required to decaffeinate coffee. Most techniques use an extraction process to remove the caffeine from the green coffee beans before they are roasted. One method starts by steaming the green beans and then rinsing them with an organic solvent, usually dichloromethane, to pull the caffeine molecules out of the beans. The other method uses supercritical carbon dioxide to extract caffeine. The latter obviously avoids the use of toxic solvents, but is energy intensive. With all extraction techniques, it is challenging to only remove the caffeine and not the flavor compounds that we want to taste in our coffee.
How is coffee decaffeinated?
Consider the chemistry required to decaffeinate coffee. Most techniques use an extraction process to remove the caffeine from the green coffee beans before they are roasted. One method starts by steaming the green beans and then rinsing them with an organic solvent, usually dichloromethane, to pull the caffeine molecules out of the beans. The other method uses supercritical carbon dioxide to extract caffeine. The latter obviously avoids the use of toxic solvents, but is energy intensive. With all extraction techniques, it is challenging to only remove the caffeine and not the flavor compounds that we want to taste in our coffee.
How many phases can be in coexistence?
A rule called the Gibbs phase rule tells us how many phases can be in coexistence for a given substance or mixture. The rule arises from the fact that, to be in coexistence, a constraint exists that the chemical potentials of each component in each phase must be equal. After some math, one can find a relationship between the number of components of a system, the number of free variables, such as temperature, pressure, or the fraction of a given component present in a mixture, and the number of phases that can be in coexistence. This relationship is, F equals Cp plus 2, where F is the number of degrees of freedom. C is the number of independent components, and P is the number of phases.
How many phases can be in coexistence?
A rule called the Gibbs phase rule tells us how many phases can be in coexistence for a given substance or mixture. The rule arises from the fact that, to be in coexistence, A constraint exists that the chemical potentials of each component in each phase must be equal. After some math, one can find a relationship between the number of components of a system, the number of free variables, such as temperature, pressure, or the fraction of a given component present in a mixture, and the number of phases that can be in coexistence. This relationship is F equals Cp plus 2, where F is the number of degrees of freedom. C is the number of independent components, and P is the number of phases.
What is the difference between a homogeneous and heterogeneous mixture?
A homogeneous mixture is one that is uniformly mixed and has the same proportions of components throughout the mixture. An example is a transparent solution of sugar dissolved in water. Specifically one in which there is no undissolved sugar floating around. A heterogeneous mixture is one that is not consistent or uniform throughout, such as a glass of sugar water with some chunks of undissolved sugar also floating around.
What is the difference between a homogeneous and heterogeneous mixture?
A homogeneous mixture is one that is uniformly mixed and has the same proportions of components throughout the mixture. An example is a transparent solution of sugar dissolved in water. Specifically one in which there is no undissolved sugar floating around. A heterogeneous mixture is one that is not consistent or uniform throughout, such as a glass of sugar water with some chunks of undissolved sugar also floating around.
Can multiple liquid phases exist for a mixture?
Yes. One familiar example is a mixture of oil and water. The immiscible oil and water phases are two different phases of liquid matter.
Can multiple liquid phases exist for a mixture?
Yes. One familiar example is a mixture of oil and water. The immiscible oil and water phases are two different phases of liquid matter.
Can there be more than one solid phase for a given substance?
Yes, solids can adopt different types of microscopic arrangements. If there is a repeating pattern to the atoms in a solid, it is called a crystal. If the ordered structure exists for the entire material, then the phase is known as a single crystal. Think of a diamond. If a sample is a bunch of individual crystals, then we refer to the material as polycrystalline. Lots of solids also just have no pattern to the arrangement of their atoms. and this class is known as amorphous.
Can there be more than one solid phase for a given substance?
Yes, solids can adopt different types of microscopic arrangements. If there is a repeating pattern to the atoms in a solid, it is called a crystal. If the ordered structure exists for the entire material, then the phase is known as a single crystal. Think of a diamond. If a sample is a bunch of individual crystals, then we refer to the material as polycrystalline. Lots of solids also just have no pattern to the arrangement of their atoms, and this class is known as amorphous.
What is the density of a material?
Density is the mass, or weight, of a material divided by a unit of volume. Water, for example, has a density of 1.0 g/cm3, 1.0 gram per cubic centimeter.
What is the density of a material?
Density is the mass, or weight, of a material divided by a unit of volume. Water, for example, has a density of 1.0 g/cm3, 1.0 gram per cubic centimeter.
How many phases can be in coexistence?
A rule called the Gibbs phase rule tells us how many phases can be in coexistence for a given substance or mixture. The rule arises from the fact that, to be in coexistence, a constraint exists that the chemical potentials of each component in each phase must be equal. After some math, one can find a relationship between the number of components of a system, the number of free variables, such as temperature, pressure, or the fraction of a given component present in a mixture, and the number of phases that can be in coexistence. This relationship is F equals Cp plus 2, where F is the number of degrees of freedom, C is the number of independent components, and P is the number of phases.
What is valence bond theory?
Valence bond theory is one of two main theories. The other being molecular orbital theory, that is used to explain bonding in molecules. Valence bond theory explains bonding by describing the interactions of atomic orbitals on individual atoms as they come together to form chemical bonds. The basic idea is that orbitals with the right shapes to overlap strongly with each other will form the strongest chemical bonds. Today, valence bond theory's description of chemical bonding based on Atomic orbitals has become less popular in favor of molecular orbital theory.
What is a triple point?
The temperature and pressure at which three phases of a substance are in equilibrium is known as a triple point. The three phases can be solid, liquid, and gas, but can also be two solid phases. Different arrangements of the molecules in the solid and a liquid phase.
What is Coulomb's law?
Coulomb's law tells us the force experienced by a pair of separated charges. It's a fundamental equation in the study of electrostatics, which is a broad area of physics concerned with the interactions between stationary charges. The key features of Coulomb's law are that it predicts an attractive force between particles of opposite charge and that this force decreases with the square of the distance between the particles. For chemistry, it's relevant to point out that the force between charges falls off rather slowly with the distance between them, so where charges are present in relatively dense materials, like liquids and solids, they have a significant effect on their environment.
What is a stable octet?
The term stable octet describes the fact that many atoms in molecules are most stable when the valence shell contains effectively 8 electrons. This counts both non-bonding electrons and electrons in chemical bonds between atoms. Molecules tend to be most stable when the valence shells of each atom in the molecule contain 8 electrons. In the Lewis structures for F2 and CH2O, see the previous question. We see that the fluorine, carbon, and oxygen atoms are each surrounded by 8 electrons. We get this total by adding both the non-bonding and bonding electrons. Since hydrogen atoms are in the first row and have just a single orbital in their valence shell, they only need 2 electrons, a single bond, to fulfill their analog of a stable octet.
What is a dielectric constant?
The dielectric constant of a material characterizes the extent to which it insulates against the flow of charge or against the effects of an electric field. Materials with a high dielectric constant screen the effects of charges within the material, while materials with a low dielectric constant allow the effects of a charge to be felt more strongly. In solutions containing ions, the dielectric constant of the solution will determine the extent to which the other molecules in the solution feel the effects of the charges present. The lowest possible dielectric constant exists in a vacuum in which there is no material present to screen the charge of a field.
What are molecular orbitals?
Molecular orbitals are different from atomic orbitals in that they cover several atoms and possibly even a whole molecule. While atomic orbitals originate from a single atom, molecular orbitals are formed from combinations of the atomic orbitals. Because they allow electrons to occupy the space between the atoms in a molecule, they can provide a very useful description of chemical bonds holding atoms together.
What is the charge of a molecule?
The overall charge of a molecule is determined by the number of protons and electrons in the whole molecule. If there are more protons than electrons, the molecule will possess an overall positive charge. If there are more electrons than protons, the molecule will similarly possess an overall negative charge. A molecule with the same number of electrons and protons is neutral and has no net charge.
What is the difference between a homogeneous and heterogeneous mixture?
A homogeneous mixture is one that is uniformly mixed and has the same proportions of components throughout the mixture. An example is a transparent solution of sugar dissolved in water. Specifically one in which there is no undissolved sugar floating around. A heterogeneous mixture is one that is not consistent or uniform throughout, such as a glass of sugar water with some chunks of undissolved sugar also floating around.
What is the density of a material?
Density is the mass, or weight, of a material divided by a unit of volume. Water, for example, has a density of 1.0 g/cm3, 1.0 gram per cubic centimeter.
What is electronegativity?
Electronegativity is a property that describes the tendency of an atom to attract electrons in a chemical bond. The most electronegative atoms are those which pull hardest on the electron density they share in a bond with another atom. There is more than one scale and definition for electronegativity, and our description here follows that given by Linus Pauling, which is the most commonly used scale in chemistry courses. Electronegativity can most readily be described in terms of the number of protons in the nucleus of the atom and the distance to which its valence electron cloud extends away from the nucleus. As a general trend, the most electronegative atoms are those with the shortest distance between the valence electrons and the nucleus. Electronegativity isn't a physical quantity that can be directly measured. but several scales have been developed that derive values for this property based on other measurable physical quantities.
What is plasma?
Plasma, the fourth state of matter, is a gas where some amount of the particles have been ionized. As little as 1% ionization leads to very different properties for plasmas than gases, including increased conductivity, like lightning, and magnetization.
What is the theory of phlogiston?
In 1667, a scientist named Johann Joachim Beecher introduced the theory of phlogiston as an explanation for the various observations scientists had made regarding combustion. These observations include the fact that some objects can burn while others cannot, and that a flame in a sealed container can go out before the combustible material is consumed. Beecher proposed that a weightless, or almost weightless, substance called phlogiston was present in all materials that could burn, and that this phlogiston was the substance being given off during combustion. If a candle placed in a closed container went out, Beecher said this was because the phlogiston from the candle was moving into the air, and that the air could only absorb a certain concentration of phlogiston before it became saturated and could no longer absorb more phlogiston from the candle. Another tenet of this theory was that the purpose of breathing was to remove phlogiston from the body. Air that had been used for combustion couldn't be used to breathe then because it was already saturated with phlogiston.
How can a fire be started with a piece of flint?
Almost everyone has seen a movie character start a fire using a piece of flint. But you may wonder how this is possible. Flint is a hard stone that can produce sparks when it is struck against a metal, such as steel. The sharp edge of the flint breaks off a small splinter of steel, which is heated significantly by the friction from the strike of the flint. As this splinter of hot steel reacts with oxygen in the air, a spark is produced. The sparks generated in this way can then ignite a piece of dry wood, paper, or other fuel.
Can multiple liquid phases exist for a mixture?
Yes. One familiar example is a mixture of oil and water. The immiscible oil and water phases are two different phases of liquid matter.
What is a phase diagram?
A phase diagram shows the phases of a particular substance as a function of temperature and pressure. An example for a single component phase diagram, as in not a mixture, is shown above. Phase diagrams also exist for mixtures, but these get very complicated very quickly.
What is molecular orbital theory?
Molecular orbital theory is the other main theory. The first was valence bond theory, used to explain and predict bonding properties in molecules. Molecular orbital theory describes bonding interactions by using molecular orbitals that are spread out over multiple atoms. And this allows an electron's location to be described by an orbital that bonds atoms together in a more realistic way than valence bond theory.
How is coffee decaffeinated?
Consider the chemistry required to decaffeinate coffee. Most techniques use an extraction process to remove the caffeine from the green coffee beans before they are roasted. One method starts by steaming the green beans and then rinsing them with an organic solvent, usually dichloromethane, to pull the caffeine molecules out of the beans. The other method uses supercritical carbon dioxide to extract caffeine. The latter obviously avoids the use of toxic solvents, but is energy intensive. With all extraction techniques, it is challenging to only remove the caffeine and not the flavor compounds that we want to taste in our coffee.
What is polarity and how is it related to molecular structure?
Polarity is related to the symmetry of the arrangement of electron density in a molecule. Polar molecules are those which possess a net dipole moment, which means that the electron density is not symmetrically distributed in all directions. Nonpolar molecules have the electron density distributed in such a way that there is no net dipole moment. Typically, this doesn't mean that nonpolar molecules have their electron density distributed evenly over every part of the molecule, but rather that the dipole moments created by an unequal sharing of electrons in each individual bond cancel each other out, so that there is no net direction in which an asymmetry of electron density exists.
How are herbal medicines prepared?
There are many ways of preparing herbal medicines. Tinctures and elixirs are extract ions of herbs using some solvent, usually ethanol. If a plant is extracted with acetic acid, the solution is known as a vinegar, even though the solvent is also vinegar. A tisane uses hot water to extract herbs like tea.
What herbal medicines do people still use today?
Aspirin and quinine are probably the most famous herbal Medicines that have made the transition to mainstream medicine. Many modern medicines were originally isolated from plants. However, but the commercial sources are now usually man-made. For example, Taxol, R. paclitaxel, was originally isolated from the Pacific yew tree. In 1967 this compound was found to be useful as a treatment for various types of cancer. For almost 30 years, most of the paclitaxel that was given to patients was obtained from the yew tree. Alternate supplies of this drug were developed in the 1990s. Moving this natural drug into the realm of modern synthetic medicines.
Who first realized that oxygen gas, O2, was required for fire?
Philo of Byzantium in the 2nd century B.C.E. was the first to observe, or at least the first to record such an observation. That if you placed a jar on top of a candle with water around its base, some water would be drawn up into the jar as the candle burned and eventually went out once all the oxygen was consumed. Although the experiment was well designed, he ended up with an incorrect conclusion about the process. Robert Boyle repeated the experiment but replaced the candle with a mouse. Seriously, and noticed the water also rose up the container. From this experiment he correctly inferred that whatever the component in air was, he called it nitroairus, it was needed for both combustion and respiration. Robert Hooke, and others, likely produced oxygen gas in the 17th century, but didn't realize it was an element as the phlogiston theory, see below, was in vogue at the time. So to really realize that oxygen gas was required for fire, it first had to be, well, discovered.
What is electrochemistry and how was it discovered?
Modern electrochemistry studies reactions that take place at the interface of an electronic conductor and a source of charged ions, possibly a liquid. The development of electrochemistry began with studies on magnetism, electric charge, and conductivity. The earliest experiments typically focused on questions surrounding properties of materials. For example, which materials can be magnetized and which materials can be charged. As early as the 1750s, scientists had discovered that electrical signals were important to human life and were using them to treat medical issues such as muscle spasms. In the late 1700s, Charles Coulomb developed laws describing the interactions of charged bodies, which are still used widely today and taught in any introductory course on electricity and magnetism. The first electrochemical cells were developed during the 1800s. Electrochemical cells are arrangements of electrodes and sources of ions that either generate electric current from a chemical reaction, or alternatively, use electricity to drive a chemical reaction. Today these cells find applications in daily life, such as in the batteries that power your car or cell phone. Today electrochemistry still constitutes an important field of research and is one that will likely continue to lead to the development of new products and technologies.
What is a Lewis structure?
Lewis structures are a simple way of depicting the electronic structure of atoms and molecules. They show us which atoms are bonded to each other in a molecule and also show how many non-bonded electrons are present in the valence electron shell of each atom. The easiest way to understand them is probably to just take a look at a few. The simplest Lewis structure is that for a single hydrogen atom, it has just one electron, and its Lewis structure looks like this. The letter H lets us know that it's a hydrogen atom, and the 1 dot represents its one electron. Here the two Fs let us know there are two fluorine atoms. The line connecting them shows that they are bonded with a single bond, containing 2 electrons. Each has 6 more electrons surrounding it, and these electrons are non-bonding. And finally, for a molecule with more than one bond, CH2O, this molecule is called formaldehyde. The Lewis structure shows us that the carbon is involved in a single bond, sharing 2 electrons with each hydrogen atom, and a double bond, sharing 4 electrons, with the oxygen atom. The oxygen atom also has 4 non-bonding electrons.
Can there be more than one solid phase for a given substance?
Yes, solids can adopt different types of microscopic arrangements. If there is a repeating pattern to the atoms in a solid, it is called a crystal. If the ordered structure exists for the entire material, then the phase is known as a single crystal. Think of a diamond. If a sample is a bunch of individual crystals, then we refer to the material as polycrystalline. Lots of solids also just have no pattern to the arrangement of their atoms, and this class is known as amorphous.
Can I think of chemical bonds as springs between atoms?
Chemical bonds can be thought of as springs holding together the atoms in a bond. When atoms in a bond are stretched or compressed from their equilibrium separation, the bond provides a force to pull the atoms back together or to keep them from getting too close. For relatively small displacements, the bond actually provides a force that is physically very similar to that of a spring connecting two objects. This model of a spring as a chemical bond can be very useful for getting an intuitive idea of how a chemical bond connects atoms in a molecule.
What is fire?
The chemical description of fire is a combustion reaction. It involves the reaction of oxygen with molecules in some combustible material. The fire itself is caused by energy released by this reaction in the form of heat and light. The fire you see is not only the light that's being released, but also glowing hot gases.
How did chemistry affect trade in ancient times?
Ancient chemistry was involved in the production of many goods that were important to trade. These included salt, silk, linen dyes, precious metals, wine, and pottery.